Welcome to AI Frontiers, where we explore the research that's building tomorrow's intelligent systems. Today we're diving into a robotics revolution where machines are learning to predict the future. We'll examine 18 groundbreaking papers published on June 24, 2025, that are reshaping robotic intelligence, from predictive mapping systems to damage-resilient machines. This is our synthesis of breakthrough research from Computer Science Robotics, exploring the frontier of embodied artificial intelligence. Picture this extraordinary reality unfolding in laboratories worldwide. A robot surgeon delicately threading coiled anchors through the chambers of a beating heart, while thousands of miles away, a Mars rover explores alien terrain, predicting what lies beyond the next ridge before it even arrives there. Meanwhile, in a research facility, a six-legged robot loses two of its limbs, but doesn't miss a step, literally reconfiguring its walking pattern in real time to keep moving forward. What sounds like science fiction is actually the cutting-edge reality emerging from robotics research. These aren't isolated achievements, but part of a coordinated breakthrough. All 18 papers we're exploring today were published on the same remarkable day, giving us a unique snapshot of where this revolutionary field is heading. Computer science robotics represents a fundamental evolution beyond traditional mechanical systems. If classical robotics was about building increasingly sophisticated mechanical puppets, computer science robotics is about creating the minds that bring those puppets to life. It's the difference between a player piano that mechanically reproduces notes and a jazz musician who understands music deeply enough to improvise, adapt, and create something entirely new in response to their environment. This field focuses on paradigm shifts in how machines perceive their world, adapt to unexpected situations, and collaborate safely with humans. We're witnessing the convergence of artificial intelligence with physical embodiment, creating systems that don't just follow instructions, but truly understand the world around them. Think of computer science robotics as a grand orchestra where each instrument represents a different discipline working in harmony. The computer vision section provides robotic eyes and environmental understanding, helping machines see and interpret their surroundings with unprecedented sophistication. The machine learning ensemble gives robots the ability to improve and adapt over time, learning from experience like biological systems. The control theory musicians ensure precise, coordinated movement and manipulation, and artificial intelligence serves as the conductor, orchestrating all these elements into coherent, intelligent behavior. We're experiencing the perfect storm of technological convergence, deep learning advances, sophisticated sensors, and intelligent algorithms, all maturing simultaneously. Our first major breakthrough involves advanced perception and mapping, where robots are learning to see beyond the visible. The SceneSense system by Achi and colleagues achieved a remarkable 75.59% improvement in mapping quality by using generative occupancy mapping with diffusion models. This revolutionary approach enables robots to predict three-dimensional occupancy maps from partial observations, like locals who know neighborhood shortcuts before seeing them. When a robot observes part of a room, SceneSense can intelligently predict what unseen areas likely contain based on learned patterns about spatial organization. Complementing this breakthrough is remarkable work in vision-based navigation, achieving sub-meter accuracy in GPS-denied environments, crucial for indoor robots and urban exploration, where satellite signals are unreliable. The second theme addresses damage resilience and adaptive behavior, tackling what happens when robots break. Two complementary research efforts demonstrate how hexapod robots can continue functioning even after losing multiple limbs. The first breakthrough involves self-modeling algorithms, enabling robots to autonomously detect leg damage using only inertial measurement unit data. Imagine a robot performing its own medical diagnosis. The second involves evolutionary gait reconfiguration, allowing damaged robots to discover new walking patterns within 1 hour of damage detection. Picture a robot losing two legs but within 60 minutes learning an entirely new way to walk that's almost as effective as its original gait. Like three-legged dogs that learn to run again, these systems could be transformative for robots in hazardous environments where maintenance is impossible, from disaster response to space exploration missions. Manipulation and dexterity breakthroughs push the boundaries of robotic hand coordination. The ManiGaussian++ framework tackles bimanual manipulation through hierarchical Gaussian world models, achieving a 20.2% improvement in dual-arm coordination. Think of teaching a robot to play piano, where both hands must work together in perfect harmony, each contributing different but complementary actions. The system learns when one arm should provide stability, while the other performs precise manipulation. Working alongside this development, the CronusVLA framework demonstrates that incorporating historical motion information substantially improves performance, reaching 70.9% success rates on challenging benchmarks. Traditional approaches treat each moment in isolation, like understanding movies through single frames. CronusVLA considers temporal context, understanding how current actions relate to previous movements, leading to more sophisticated manipulation strategies. The numbers tell compelling stories across our research themes. Predictive mapping's 75.59% improvement enables significantly safer exploration by allowing robots to anticipate obstacles and plan better routes. Damage resilience research shows 1-hour recovery times from catastrophic limb loss, crucial for mission-critical applications. Zero-shot electromyography interfaces eliminate calibration requirements, enabling instant prosthetic control through muscle signal detection. Temporal awareness provides a 12.7% performance boost simply by considering motion history rather than isolated moments. Safety verification methodologies demonstrate that formal mathematical methods can successfully validate agricultural robot safety in dynamic environments. These aren't just incremental improvements, they represent fundamental shifts in robotic capabilities, moving from reactive systems to truly intelligent, adaptive machines. Our paper of the day explores the revolutionary work by Aki and colleagues on robust robotic exploration and mapping using generative occupancy map synthesis. This research represents perhaps the most significant paradigm shift in robotic mapping since the introduction of simultaneous localization and mapping decades ago. The core innovation treats occupancy mapping as a generative problem, rather than purely observational. Traditional robotic mapping operates on the principle that robots can only know what they directly observe through sensors. This paper fundamentally challenges that assumption by introducing generative artificial intelligence into the mapping process, enabling robots to make informed predictions about unobserved areas based on learned patterns about spatial organization. It's like the difference between tourists with basic maps versus local residents who understand neighborhoods deeply enough to predict shortcuts and anticipate obstacles. The technical implementation involves sophisticated components working in harmony. The researchers developed diffusion models specifically designed for three-dimensional occupancy prediction, trained on diverse environmental data to learn spatial organization patterns. The system operates on voxelized three-dimensional representations, learning to denoise corrupted occupancy maps through iterative processes. This leverages the same mathematical principles powering modern AI image generators, but adapted specifically for three-dimensional spatial reasoning. During exploration, when robots encounter partially observed environments, the system takes sensor observations and uses learned diffusion processes to generate multiple plausible completions of occupancy maps. These predictions are probabilistically fused with running occupancy maps, with confidence weights based on uncertainty estimates. The system doesn't make blind predictions, it quantifies confidence and adjusts reliance accordingly. The real-world impact extends far beyond laboratory achievements. Consider search and rescue operations in partially collapsed buildings, where robots need to navigate safely while searching for survivors. Traditional mapping approaches require robots to physically explore every area, potentially exposing them to dangerous structural instabilities. With predictive mapping, robots can make intelligent inferences about structural patterns, identify promising search areas, and plan safer navigation routes based on learned architectural principles. Mars rovers could predict terrain characteristics before physical exploration, identifying safe paths and interesting geological features. This cross-pollination between generative AI and robotics opens unprecedented opportunities for innovation. The approach demonstrates how modern artificial intelligence techniques can be effectively adapted for robotics applications, creating new research avenues at the intersection of machine learning and embodied intelligence. We're witnessing the dawn of anticipatory robotics, where systems move from reactive responses to predictive intelligence. These robots don't just respond to immediate sensory input. They anticipate, predict, and plan based on learned understanding of how the world works. It's like the difference between gardeners who react to seasonal changes versus those who understand natural cycles deeply enough to prepare for seasons before they arrive. This shift toward predictive robotics could revolutionize applications from autonomous vehicles that anticipate traffic patterns to manufacturing robots that predict optimal assembly sequences. The integration of generative artificial intelligence with physical embodiment creates safer, more efficient autonomous systems. Rather than waiting for problems to occur, these systems can anticipate challenges and proactively adapt their behavior, leading to more robust and reliable robotic applications across diverse domains. The intelligence revolution in robotics continues accelerating across 6 transformative themes reshaping the field. From advanced perception, enabling predictive environmental understanding, to safety verification, ensuring reliable human-robot collaboration, we're witnessing unprecedented convergence of capabilities. Aki and colleagues' work on generative occupancy mapping leads a paradigm shift from reactive observation to predictive intelligence, fundamentally changing how robots understand and navigate their environments. This convergence creates robotic systems capable of operating in chaotic, unpredictable human environments rather than carefully controlled factory settings. The transition from mechanical automation to true artificial intelligence in physical form represents one of the most significant technological developments of our time. These 18 papers demonstrate that the future of intelligent machines isn't approaching. It's unfolding right now in laboratories worldwide. This comprehensive research synthesis was created using advanced AI systems to ensure accuracy and accessibility. The analysis utilized Claude Sonnet for 20250.514 for research synthesis and content generation, providing expert-level understanding of complex technical papers. Text-to-speech synthesis is powered by DeepRAM technology, delivering natural, professional narration optimized for technical content. Image generation utilizes OpenAI systems to create relevant visual representations supporting the research discussion. All content underwent human expert review for technical accuracy and clarity, ensuring reliable information delivery. Complete academic references are provided for all discussed papers, though potential oversights in citation formatting may occur despite careful attention to detail. Thank you for joining us on AI Frontiers, your gateway to tomorrow's intelligence. Subscribe for cutting-edge AI research synthesis and daily insights from the frontiers of artificial intelligence. We provide expert analysis of breakthrough papers and emerging trends, helping you stay ahead in this rapidly evolving field. Join our community of forward-thinking researchers, developers, and tech enthusiasts who understand that the future of AI unfolds here first. In this podcast, we bring you the latest breakthroughs in computer science and AI, straight from archive preprint server. From neural networks to quantum computing, we simplify complex research so you can stay ahead. Whether you're a developer, researcher, or tech enthusiast, AI Frontiers keeps you informed daily. Thanks for listening. If you enjoyed this episode, subscribe for daily updates. See you tomorrow with more cutting-edge AI insights. Disclaimer: this video uses archive preprint server content under its API terms of use. AI Frontiers is not affiliated with or endorsed by archive preprint server.